Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 12, Organic Chemistry 1. Today we will continue on structure and stereochemistry of alkanes and cycloalkanes. We will start by solving some problems. For each pair of compounds, identify whether they are constitutional isomers or two representations of the same compound. Where Atini, they give us the two structure. Here they are. So what you have to do is to name the structure using IUPAC. For the first one, we selected long chain. This is a long chain. And we number from here 1, 2, the shortest way to substituent. We will find out that the name is 2,3-dimethylbentane. For this structure, again, we selected the long chain, 5 carbon chain, and again, when we name it, give the number 1, 2, 3, 4, 5, we find out that the name is 2,3-dimethylbentane. It's the same name. So these structures have the same name, and therefore they are two representations of the same compound. Another two compounds. For that one, okay, it's 1, 2, 3, 4, 5, 6, 7. And when we number 1, 2 to get to the shortest way to the first substituent, here is methyl and here is propyl. So that's 2-methyl-4-propyl. Get to that one. For that one, we have here long chain, 7 carbon, but we have one substituent. If we select the same length, 7 carbon, this way, we will find out that we have two substituent. Which one we select? The one with more substituent. That's fine. Then we start number. Start from here or here. If you start from the right, that the number will be 1, 2, 3. So we have 3-methyl, 4-propyl. If we number from the other side, from left to right, so it will be 1 in here, we will find out that the propyl will be 4, the same, but the methyl will be 5. The IUPAC said select the shortest way. So this is the shortest way. And the name of the compound will be 3-methyl-4-propyl-heptane. And the first one is 2-methyl-4-propyl-heptane. Two different names. So these compounds have different names. Therefore, they are constitutional isomers. They are constitutional isomers. Type of carbon atoms in a molecule. We were talking about the red carbon. This carbon connected to only one carbon in this structure, right? So it is primary carbon, connected or bonded to one other carbon. In this case, this carbon is connected to 2 carbons, so it is secondary carbons. Here, connected to 3 carbons, so it is tertiary carbon. Here is connected to 4. This is quaternary carbon, quaternary carbons. For a compound containing only one carbon, like methane or methyl chloride or methanol, are not classified. You cannot classify it as primary or secondary or tertiary. It doesn't apply to them this name because no carbon is connected to this carbon. No carbon is connected. Okay, let's see this carbon. This carbon is connected to 3 carbons. So this carbon is tertiary. This carbon is connected to 2 carbons. So this carbon is secondary. Relative stability of isomeric alkane. We talked about constitutional isomers, right? But which one is more stable than the other? In order to compare the stability of constitutional isomer, we look at the heat liberated when they each undergo combustion. لو أنا حرقت المركب الكيميائي هو ليه نفس الموليكولار فورمولا. لو أنا حرقته يعني أنا get final product carbon dioxide and water. And get the constitutional isomer like C8H18, it will give the same number of moles of carbon dioxide and water. The difference will be the heat evolved of this reaction. لو كان الهيت كونتنت بتاعها بسيط يعني كانت ستيبل يبقى الطاقة اللي طالعة منها هتكون قليلة. The compound is stable. المركب ثابت طاقته الكامنة بسيطة. If the heat content is high, this means that it's higher in energy and will release more energy when it turn out to be carbon dioxide and water. We will find here from the experimental data that the octane, normal octane, release high energy than the more substituted alkane 2233 dimethyl tetramethyl butane. So the more branched, the more stable. The more branched, the more stable. How we can get this? By study the heat of combustion. The more substituted alkane will release less energy.
Flammable and combustible liquids. Previously, we've mentioned that the main source of alkanes is petroleum. By refinery procedures, the most important product, namely the gasoline fraction C5C12, can be isolated in approximately 19% of the crude oil. A lot of emphasis was placed on procedures that produce a high octane rating blending stock, C5 to C12 gasoline alkanes fuels. Octane number, also called octane value or octane rating, is one of the critical measures of gasoline's performance. It is a measure of a fuel's resistance to knock or to ignite prematurely. The standard liquids used for the octane number tests are N-heptane, which have very poor knock resistance and is thus assigned a value of 0, and isooctane 2,2,4 trimethylpentane, which exhibits excellent knock resistance and is thus assigned a value of 100. The anti-knock performance of the fuel being tested is then compared to mixtures of the two standards. If its performance is equivalent to a mixture that is 80% isooctane and 20% N-heptane, it would have an octane number of 80. There are several hydrocarbon compounds and even some commercial gasolines that have octane numbers greater than 100. This is done by adding tetraethyl lead to pure isooctane. The yield of useful gasoline can be improved in 2 ways. Number 1. Cracking is a process by which carbon single bond carbon bonds of larger alkanes are broken, producing smaller alkanes suitable for gasoline by means of heat and usually pressure and sometimes catalysts. Number two, reforming is a process in which straight-chain alkanes are converted into branched hydrocarbons and aromatic compounds which exhibit less knocking during combustion.
How to write 3D structure? There are several conventions for drawing a 3D molecule on a 2D surface. Let's take an example, ethane. This is a molecular model of ethane. Okay, it's two carbon, and each carbon has three hydrogens, and the carbon-carbon bond. The first type is Dash-Line-Wedge. Line on the plane of the paper. Wedge in front. Dash or dot in the back. See, if I'm holding the molecule where this hydrogen, carbon, hydrogen in one plane, this I think to you it will be front, and this will be in the back. This will be in front, and this one in the back. Okay, so you draw this, the one in front this way, the one in the back dashes, the one in the plane solid line. Now if I'd like to draw another type, they call it Sawhorse projection. I tell this a little bit 45 degree and look to the molecule from the up, okay, and draw it. So this one and this one, this is in front will be this one, and this is in the back will be that one. Carbon, carbon, single bond. The one in the back will be this way, in front this way, and this one will be the one on the line. This is a line. Okay, but it's not really so popular to use this projection only for small and very simple molecules. Fischer projection. The Fischer projection depends on the center carbon here. I think this one will be in front and this is in the back. So let's do it. I would like this to be in the back to you. Okay. Now these two are in front and these two to you in the back. Okay. The one in front, okay, I'll put them east and west. And the one in the back, okay, up and down will be north and south. So I hold the molecule this way. This is the center I am holding. This is up and this is up. So this one will be east and west. This is in the back up and this is in the back down, will be north and south. And if this one is frequently seen when we start drawing biological molecule in biochemistry, like amino acid, saccharides, etc. Another type of projection called Newman projection, molecule viewed along the CCX. So if you are looking for the molecule from this side, you will see this atom in front, and you will see that bond. This front atom. The one in the back is not showing. You do the circle, and then you show the bond in the back. So these are the front carbon, and these are the hydrogen connected to the carbon in the back. Draw a bond line structure for the following compound. This is a Newman projection for the compound. I'd like to transfer this structure, Newman projection, to a line structure. We recall that this is the front, okay? So I first transfer this to what we call it Sawhorse type structure. This is the front carbon carrying 2 CH3, 1 CH3, 2 CH3, and 1 H. So that's CH3, CH3, and 1 H. Now from this carbon connected to one in the back, all right? This is a carbon in the back, okay? This carbon is carrying CH3, okay? This is CH3, and ethyl group CH2, CH3, okay? This is CH2, CH3, and again one more CH2, CH3, all right? CH2, CH3. Now, if you would like to write the line, okay, I have carbon carrying 2 CH3, okay, and carbon in the back carrying 1 methyl and 2 ethyl group. Okay, here is the structure of the compound. It is 3 ethyl, 2,3 dimethyl pentane. All right. Determine whether the following compounds are constitutional isomers. Given are two structures in Newman projection, we will transfer this to line structure and give each structure a UBAC name and then compare. Now we have this carbon in front. This carbon is carrying isopropyl group, hydrogen, CH3. Then carbon in the back is carrying 3 hydrogens. All right. Now we have here carbon carrying CH3. This carbon is carrying CH3, carrying CH3, carrying isopropyl group. This compound is 2,3-dimethylbutane. Come to this one. This carbon here, carrying 1 H and 2 CH3, carrying 1 H and 2 CH3. The carbon in the back, carrying 2 CH3 and one hydrogen. So the structure would be carbon carrying 2 CH3 and carbon in the back carrying 2 CH3. The compound is 2,3-dimethylbutane. Oh, they are same compound. It is one compound with different way of drawing. Conformation analysis of alkane. أول مثال ethane. If we look for ethane and draw it in Newman projection, we will find that for this particular one, the Newman projection here is the front carbon, hydrogen, hydrogen, hydrogen. As you can see, the carbon in the back carrying the 3 hydrogens, and the dihedral angle between this and this, okay, is 60 degrees. It's carbon single bond carbon. So what we expect free rotation. If we move this 60 degrees, see, now the hydrogen are very close to each other with dihedral angle equal 0. We will have in this particular conformer what we call eclipsing interaction or torsional strain. الالكترونات بتاعت الكربون هيدروجين سيجما بوند هيبقى فيه تنافر بينها وبين بعض. تاني حاجة فاندر فال radii for this hydrogen will repel each other again. Okay? So, in the staggered form, where the hydrogen dihedral angle is 60 and that 2 red hydrogen has 180 degree, okay, the energy is low. When we rotate 60 degree, now we have conformer with high energy, eclipsed form. Again, 60 degree will go back to the staggered. 60 degree we get to eclipsed. One more time, 60 degree. We'll end up with staggered form. 60 degree. Eclipsed form. Okay? The difference in energy between eclipsed form and staggered form is 12 kilojoule per mole. If you look for the conformer structure, we have 3 eclipsed interaction. 1, 2, 3. So if the total is 12, each hydrogen eclipsing interaction will be 12 by 3, so it is 4 kilojoule per mole. The next example is propane. We will look from here, from this carbon to that carbon. So the first carbon in front of your eyes will have CH3 and 2 hydrogens. Okay, so CH3 and 2 hydrogens. Okay, if we have the CH3 up and the H down, and the dihedral angle between CH3 and the H 60 degree, okay, that will be stable form. Okay, now if we go and rotate 60 degree, CH3 will hydrogen will have 0 dihedral angle and unstable, higher in energy conformer. We rotate once again 60 degree, the CH3 again will be between 2 hydrogens with 60 degree and stable once again. 60 degree will go back higher in energy, okay, where the CH3 and the hydrogen will repel each other, and going again, CH3 will go back to stable. 60 degree will be higher conformer in energy. Between the higher energy conformer and the low energy conformer is 14 kilojoule per mole. Remember from the previous ethane conformers, we said that we have eclipsing interaction of 4 kilojoule per HH repulsion. Okay, now we have 1, 4, 1, 4, and the total of 14. So 14 minus 4 will give us 6 kilojoule per mole for the eclipsing interaction between the CH3 group and the hydrogen atom. For butane, 4 carbons, okay, if we look for the carbon 2 and 3 and draw Newman projection, we will find out the front carbon carrying CH3 and 2 hydrogens, and in the back again CH3 and 2 hydrogens. This conformer, when you have CH3 and CH3 180 degree, we call this anti-conformer, and that has low energy. When we start moving 60 degree, we will have eclipsed form, and that's high in energy. And in this conformer, you have the eclipsed form between CH3 and the H, CH3 and the H, okay, and H and H. You move that again 60 degree, you will get up with another form conformer where the CH3 and CH3 60 degree. All right. Then once again 60 degree, you will have here eclipsing between CH3 and CH3. In this one we have CH3 and H, CH3 and H. Here the eclipsing between CH3 and CH3, and that will have the higher energy. Okay, higher energy. We move again 60 degrees. We go back the same as this one, where CH3 and CH3 have 60 degrees. Okay, and then we move again 60 degrees. We go up where we have CH3 eclipsing with hydrogen, CH3 eclipsing with hydrogen, and hydrogen is eclipsing with hydrogen. This one and this one, they are the same in energy. Okay, so staggered conformation about single bond are favorable over eclipsed conformation. Okay, the staggered is the most stable, right? Van der Waal repulsion between non-bonded hydrogen, these two, okay, they are non-bonded together, okay, but they are close to each other in space, so they have repulsion force. Occur when atoms are squeezed closer together than the sum of their van der Waal radii. الفان der Waal radii هي عباره عن كاني انا بتخيل حاجه من واحد يعني ايه الساينس متخيلينها ان الهيدروجين دي ايماجينري في السبيس لها فراغ معين، حجم معين. خلاص، الحجم بتاع الهيدروجين دي والهيدروجين دي قربوا لبعض، فحصل ايه؟ ريفولشن. كأن ايه؟ المفروض ان هو محدش يعدي من الحته دي، لكن هم عدوا بالايه؟ بالضغط. اوكي؟ alright. Conformation containing van der Waal repulsion are less stable than the conformation in which the repulsion are absent. هنا مفيش الريبولشن دي موجودة. اوكي؟ الريبولشن موجودة هنا، موجودة هنا. اوكي؟ Rotation about carbon single bond in most cases is so rapid that it is hard to imagine separating conformations except at very low temperature. In each case below, identify the highest and lowest energy conformations. In case where 2 or 3 conformations are degenerate, draw only one as your answer. Here is the 3 methyl hexane in this configuration. If you look for this molecule between carbon 3 and 4, you will find carbon 3 is here, is carrying CH3. It's in the back. So when you look at it, you will find the CH3 on your left hand and the hydrogen on the right hand, CH2, CH3, like this. Carbon 4 has 2 hydrogens and 1 ethyl. If the 2 bulky ethyl group are anti to each other, that will be the lowest inner conformation. If the CH3, CH2 are eclipsing together and the ethyl is eclipsing to the hydrogen and the hydrogen eclipsing the hydrogen, that will be higher in energy. But if the 2 bulky ethyl groups are eclipsing together, this will be the highest energy. The same molecule, but in another enantiomeric form, this one, 3-methyl hexane, the CH3 on carbon 3 will be on your right hand and the hydrogen on left hand, Again, if the CH2CH3 and the CH2CH3 on carbon number 4 are anti to each other, that will be the lowest energy, and if they are eclipsing each other, that will be the highest energy. See you in the coming lecture.